Today, we explore the most fundamental and yet most misunderstood concept in science: energy. We'll trace its meaning from ancient philosophy to cutting-edge physics, and uncover how it shapes everything from stars and cities to your body and brain. So sit back and let's dive into Chapter 1, Energy in Our Minds, Concepts and Measures. Let's begin with a deceptively simple question. What is energy? The word energy originates from ancient Greek, energeia, coined by Aristotle. It's a combination of en meaning in and ergon meaning work. So literally, energy is the potential to act, to move, to do. To Aristotle, energy wasn't some invisible force. It was actuality, a thing's essential function. But for almost 2,000 years after, our understanding didn't progress much. Even in the 1700s, great thinkers like David Hume called energy one of the most obscure and confusing ideas in all of metaphysics. So what changed? In the early 1800s, things started to shift. Scientists began asking a new question, not just what is energy, but how does it behave? Thomas Young was one of the first to define energy scientifically. His equation was off, he didn't have the mass, but it was a start. Then came Sadi Carnot, who studied how heat engines worked. He found that there were limits to how efficiently you could turn heat into motion, a discovery that would soon form part of the laws of thermodynamics. But the real breakthrough came from Julius Robert Mayer. In the 1840s, Mayer noticed something strange. The blood of patients he treated in hot tropical climates was brighter red than in cooler Europe. Why? Because their bodies needed to burn less food to stay warm. That insight led Mayer to a bold idea, one that changed physics forever. He proposed that heat and work are equivalent forms of energy, and that energy could neither be created nor destroyed. This would become the first law of thermodynamics, the conservation of energy. Then James Prescott Joule took it further. Through meticulous experiments, he measured how much mechanical work it took to heat water. His findings confirmed Mayer's theory. Energy is conserved and it can change forms, but the total always stays the same. Let's pause for a moment and review the three major laws that govern energy. First, the law we just covered. Energy can't be created or destroyed, only transformed. Second, the law of entropy. Discovered by Rudolf Clausius in the 1850s, it states that energy naturally spreads out. In other words, the universe trends toward disorder. Once high-quality energy, like fuel or food, is used, much of it becomes low-quality heat, and that heat can't be fully reclaimed. Third, the law of absolute zero. As you approach minus 273 degrees Celsius or 0 Kelvin, all molecular motion halts. That's the coldest possible temperature, and at that point no more energy transfers can happen. These three laws underpin everything from your car engine to the fate of the cosmos. Here's the strange part. Even with all this scientific knowledge, we still don't really know what energy is. Nobel Prize-winning physicist Richard Feynman once said, "It is important to realize that in physics today, we have no knowledge of what energy is. Instead, energy is best understood as an abstract quantity, something we calculate, measure, and observe in action. It's not a substance or a visible thing. It's the ability to cause change, to move, to heat, to grow, to glow. Even when you're sitting still, your body is using energy. Your heart is pumping, your lungs are breathing, your brain is sending electrical signals. All of that requires energy from food. So, when someone says, "I feel energized after a workout," they're not being scientifically accurate. In reality, they've used energy, but feel better thanks to endorphins, not some mystical new supply of power. Let's talk about the different forms energy can take. First is kinetic energy, the energy of motion. A moving car, a falling rock, or a gust of wind all have kinetic energy. Then there's potential energy, stored energy due to position or condition. Think of a stretched spring or water behind a dam. Thermal energy is heat, the vibration of atoms and molecules. Chemical energy is stored in the bonds of molecules, like in food, wood, or gasoline. When you digest or burn them, that energy is released. Electrical energy is the flow of electrons, what powers your devices and lights. Nuclear energy comes from splitting or fusing atoms, and electromagnetic energy includes light, radio waves, X-rays, even the warmth of the sun. These forms can all convert from one to another. For example, sunlight, which is electromagnetic, powers plants, which is chemical, which we eat for fuel, also chemical. And we burn that in our muscles, turning it into kinetic and thermal energy. Now, how do we measure energy? In the metric system, the standard unit is the joule. 1 joule is the energy used when a force of 1 Newton moves something 1 meter. Power, the rate at which energy is used, is measured in watts. 1 watt equals 1 joule per second. Here's a fun example. If you lift an apple 1 meter off the ground, you've used roughly 1 joule of energy. Do that every second and you're working at 1 watt. But, everyday activities use far more energy. The average adult uses around 100 watts just to stay alive. That's your basal metabolism. A microwave oven? About 1,000 watts. A hairdryer? 1,500 watts. Because these units are small, we often use prefixes. Kilo means 1,000, mega means 1 million, giga means 1 billion, and tera means 1 trillion. So a megajoule, or MJ, is 1 million joules. Energy spans an enormous range. For instance, a small bird needs about 50,000 joules a day just to survive. Meanwhile, a car engine can use 50 million joules in a single trip. Now get this, a thunderstorm releases over 100 trillion joules. And the sun? Well, it emits about 400 septillion joules every second. To manage these extremes, we use both large prefixes, like terajoules and exajoules, and small ones like microjoules and nanojoules. For example, typing a key might use 2 millijoules. A flea's hop might be 100 nanowatts of power. And a spacecraft engine, it can fire with megawatts of thrust. Not all energy conversions are created equal. Photosynthesis, for example, is terribly inefficient. Most plants convert less than 0.3% of the sunlight they receive into biomass. Crops may reach 4 to 5% at best. On the other hand, electric resistance heaters are nearly 100% efficient. Every joule of electricity becomes heat. Humans digest carbohydrates with about 99% efficiency. Natural gas furnaces can reach 95 to 97%. And modern electric motors convert 95% of their input into motion. Still, the second law reminds us, every time energy is converted, some of it becomes unusable, typically as low-grade heat. That's entropy in action. In everyday life, you may hear about calories in food. 1 kilocalorie equals 4,184 joules. Kilowatt hours on your electricity bill. 1 kilowatt hour is 3.6 million joules. British thermal units, or BTUs. 1 BTU equals about 1,055 joules. You might also hear horsepower, an old unit where 1 horsepower equals about 745 watts. These units are historical leftovers, but they all describe the same thing: energy, whether it's lighting your home, charging your phone, or fueling your body. Finally, a powerful concept: power density. How much energy is used or produced per unit of area? Sunlight reaches Earth with a power density of about 170 watts per square meter. That's our biosphere's fuel. Cities, machines, and people concentrate energy use into dense zones. A factory, for example, might consume thousands of watts per square meter. Comparing these values helps us understand what technologies are practical, how much land we'd need for solar panels, or how efficient our systems are. It's also a reminder that while the sun delivers thousands of times more energy than we use, harnessing and converting it at scale remains a major challenge. So what have we learned? Energy is complex, abstract, and all around us. It flows through our bodies, powers our civilizations, and shapes the universe itself. But to understand it, to use it wisely, we need to measure it, respect its limits, and appreciate its transformations. This chapter lays the groundwork for everything to come. In the next episode, we'll look at how energy flows through nature itself, from sunlight to ecosystems. If you enjoyed this deep dive, don't forget to like, subscribe, and share.